Alright guys, so today we're going to talk about properties of definite integrals. And these are just a couple of things to watch out for. Usually there are a few AP questions on this. But we're just looking at different kind of rules, general rules. Some of these we already know already. So like the first one is if we multiply a function by a constant when we take the integral, we can always just take that constant outside. So this is the same as c times the integral from a to b of f of x dx. So an example of that would just be if we had the integral from 0 to 1 of 3x dx. We can bring the 3 outside and we can write this as 3 times the integral from 0 to 1 of x dx, and then we're able to take that integral of x. This rule is not always necessary, but it can be helpful, especially with u substitution. The next rule we have is integrating a sum. And again, we've talked about this one as well. But so when we have two functions that are adding together, or you could be subtracting them, we can split that up into two different integrals. So this is the integral from a to b of f of x dx plus the integral from a to b of g of x dx. And this is extremely helpful when we get something like x plus 1 over x squared dx, and then we can break this up to be the integral from a to b. So we can break that up to be x over x squared plus 1 over x squared dx, and then we could further break it up into two integrals if we want, from a to b of 1 over x dx plus the integral from a to b of 1 over x squared dx. So that's the sum one. The last one is some new ones for us. So these are all additive properties. The first one is that if we add the integral from a to b of f of x dx plus the integral from b to c of f of x dx, and we'll notice that the b is being repeated. So if we graphed this, right, we have some curve f, and we're trying to find the area under the curve from a to b, right, that's this one. So from a to b, that's this area right there. And then from b to c, right, would be, let's get another color. From b to c, we'll start now at b, and we'll go to some new point c, and that'll be this area over here. And so if we add both of these together, you guys can kind of see in just a little bit of geometry, we'll show you that this is the same as from A all the way to C, all of that. So when we add these, right, the B is an upper limit and then a lower limit, right, it's being repeated. That's going to go away, and we're just going to go from A, right, we're starting at A, going to B, repeating B, going to C. So we're going to go from A to C of f of x dx. And this one almost always shows up somewhere on the AP test. I guess it's nice, if you know one of these two, right, and then it can help you to solve. You can also go backwards. So if we start off with from A to C, you could go backwards and say this is from A to B f of x dx plus the integral from b to c of f of x dx. So this could be helpful, like say a problem tells you that from 4 to 9 f of x dx is equal to 10, and then you know that from 4 to 6 f of x dx is equal to 6. So you could solve this, and we could say, okay, if we go from 4 to 6, then we also need to go from 6 to 9, and that'll be equal to the full integral from 4 to 9. And then a little bit of substitution would be 6 plus integral from 6 to 9 is equal to 10. And we subtract and we get that the integral from 6 to 9 is equal to 4. So that's the addition kind of with different endpoints or different intervals. Then the last one is going to be any integral where the lower and upper bounds, oh no, we have two more, sorry. The lower and upper bounds are the same. And so if we think about this, this is going to be a graph where, again, here's our some curve f. And this is a graph where we're going from A to A. So you can't make that, geometry, you can't make that into a 2D surface because there's no width. So it would be like, the area, if we did a Riemann approximation, your length times width, well, the width would be 0. So when we have this endpoint repeated, the integral is always equal to 0. So, any example we want, the integral from 3 to 3 of cosine e to the x cubed over ln of x plus 74x, right? Since we went from 3 to 3, this is just equal to 0. So any integral where the interval does not change is equal to 0. And then finally, our last one is going to be that the integral from a to b of f of x dx is always equal to the negative, the opposite of the integral from b to a of f of x dx. So if you switch your endpoint, then the integral switches signs. The reason this happens is that on our curve, we're doing area underneath the curve, but we're thinking we're going from this lower point A to this upper point B. So we're reading left to right. Well, if we now call this the lower point and this the upper point, right, where we switch it, we have B lower and A upper, we're now going backwards. And so we're kind of like erasing what we had. So we make it negative. And you could test that out. So really easily, if we just did from 3 to 4 of, say, 2x dx, we'll get this integral is 2x squared over 2 from 3 to 4. The 2's cancel. And we get 16 minus 9 is equal to 7. Now if we do this backwards, right, that would be the integral from 4 to 3 of 2x dx. Again, we get 2x squared over 2. But now we're going lower limit of 4, upper limit of 3. And 3 squared is 9 minus 16. So you see when our endpoints change, this order of subtraction changes, and we get negative 7. So there's that. Generally, you don't want to write it with you almost never ever want to write in calculus the higher interval on the bottom. So what would happen is if you got a question where it says, what is the integral from 10 to 3 of x squared dx, it's just generally common practice that you would want to rewrite this as the negative integral from 3 to 10 of x squared dx. And that's just generally how we like to write it in calculus. So those are the properties of definite integrals, and have a good night, and I'll see you guys in class tomorrow.